We have here some area in which we have a magnetic field which is pointing in the blackboard. We have an initial field pointing in the blackboard which is 0.8 Tesla. And we have the BDT, the magnetic field is gradually becoming smaller and smaller, weaker and weaker. That's why we have the minus sign of 0.045 Tesla per second. This is the field is decaying, so to speak. So if you want to know what B is at any moment in time, you would have plus 0.8, if I call plus going into the paper, minus 0.045 times T. And if you wait long enough, then the field will even reverse. It will come out of the paper. We have right here, concentric, a wire loop. The wire loop has a radius r. Oh, that's actually a terrible thing to do. Let's not do that. Let's give this a radius a. No, oh, let's not do that either. Let's give it a radius d. And let's give the resistance of this wire a capital R. Otherwise we get too much confusions. This is point A, and this is point B on that wire. Well, the resistance of the wire is uniformly distributed, and we are now asked what is the induced current in this loop when this magnetic field is slowly decaying. First of all, what is the meaning of this minus sign in this equation? We also refer to that minus sign sometimes as Lenz's law. The meaning is the following, and once you understand the meaning, you can actually, in your calculations, completely forget the minus signs. You will see why. The meaning is the following. The magnetic field, in this case in the paper, is gradually decreasing. The induced current in this loop will now try to oppose the change. And the change is that the magnetic field, which is in down direction, gets weaker and weaker and weaker. The system opposes that, and therefore the system will try to keep the field pointing in the paper as much as possible, and the only way it can do that is by driving an induced current in clockwise direction, because that will give you an induced B field in this direction, which will oppose the change, namely that the B field becomes weaker and weaker and weaker. So inside this wire, there must be an electric field that must be building up, which will be driving this current. Now, we're now going to apply Faraday's law. Big moment in our life. Closed loop integral of E dot dl. This is my loop. What is my surface? Open surface attached to the loop. I might as well choose this one. Radius little d. This now, we call that the EMF. Acts like a battery. There is no battery in there, but yet there is an electric field that is generated and there is a current flowing. We call that the EMF. Electromotive force. That now equals minus dB. dB dt times pi d squared times this surface, because B is the same everywhere inside this surface, so it's very easy to execute the integral. That also equals E, which is the electric field, times 2 pi times d. Because when I go around, E dot dl, E is the same everywhere, so you get E times 2 pi d. Now I would suggest that you forget about minus signs, that you take absolute values everywhere, because we already know that the induced current is in this direction. So there's really no need to carry any further these minus signs. You know what the BDT is. You know what D is. So you calculate what the EMF is. So you can calculate what E is, because you know what D is. And so now you have the EMF, and you can now calculate that the induced current is that EMF divided by the resistance R of the wire. And so this allows you to calculate what current is going to flow. So far, so good. I don't think you're going to have a problem up to this point. But now comes the part where it becomes very non-intuitive. Young is asking you, what is the potential difference between point A and point B? And that is a nonsense question, because it depends on the routing, how you go from A to B. I would like to make a different drawing to make my point as clear as I possibly can. Here is only that inner loop. Here is point A, and here is point B. And the electric field, I'll put it in red now, is in this direction, this direction, this direction, this direction. Notice that the integral of E dot dl is not zero, it's a non-conservative field. Kirchhoff's law no longer holds. But now comes the non-intuitive part. If I march from A to B along this line, then the integral in going from A to B of E dot dl is positive. You can see E and dl are in the same direction, and it happens to be, if I did not make a mistake, plus 0.7 millivolts. If, however, I walk in this direction, notice that my E and my dl are in opposite directions, so the dot product will give me a minus sign, and so here the integral in going from A to B of E dot dl is negative. It happens to be minus 0.7 millivolts. Suppose I walk this way, exactly through the middle, then the integral of E dot dl from A to B, E dot dl equals 0. If I put the line slightly here, the trajectory, the path, will be larger than 0. If I put it on this side, it will be smaller than 0. So you see, it is completely ill-defined. I can go even further and show you the absurdity of Young's question. If I have here point A, and I have here point B, and if I choose a closed loop which starts at A and goes around and 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 around, and finally attach it to point B, then it's a closed loop, and I do that 100,000 windings, then the integral from A to B of E dot dl, believe it or not, is plus 700 volts. That's to say, if I start in this direction. If I start in this direction, then it is minus 700 volts. Can you now say that A is at a 700 volt potential higher than B? That's nonsense, because you go this way, then it is 700 volts below B. Now, how real is this 700 volts? Can you actually measure these voltages? And the answer is yes. If, for instance, in my previous example, if I had a wire here, and I had a voltmeter here, straight through the middle, this voltmeter would read 0. If I had a wire here, and a voltmeter here, and attach it here, this voltmeter would read plus 0.7 millivolts. Was it 0.7? Oh no, it was 7. If I had a voltmeter here, in this line, then this one would read minus 7 millivolts. And if I put a voltmeter here in this line, which has 100,000 windings, that voltmeter would read me plus 700 volts. That's the whole idea behind transformers. So, I hope it will stick that the concept of potential difference between 2 points is no longer defined when you deal with a non-conservative field, and that's always the case when the magnetic flux through a surface attached to a closed loop is changing. And it is sad, truly sad, that Young does not understand that.